The goal for our final project was to build a robot that would climb the ladder made out of totally pneumatic parts. We were supplied effects, robotic system, and any 3D parts we made. The expectation was to start at the 4th rung, no higher, and climb every rung to the top, at least 1 foot at each rung once. There did not have to be a start button or a stop button. It just had to make it up the 6 rungs. Here's our initial design that we created. We started out with 2 side wheels. And all they are is guide wheels for the project to slide up the rails of the ladder. There is no mechanical advantage to them. Secondly, we have 2 feet of a single double acting cylinder. The first foot is our idler foot. And what that does is it is a spring action foot that will lock and hold the robot in place once it is brought up to the next rung. The top foot, hooked to our double acting cylinder, is the one that actually does the lifting until the other foot kicks in so it can move to the next rung. So this was how it was built between our group. This will be the electrical side first. For the electrical side, we got 24 volts going to our Festo easy port. We ground all of our boxes, ground and power, ground, power. Both of our switches or read sensors are grounded and powered together right here and right here. Then we, in the normal position, our lower read sensor is on, which is then signal is brought over to the detent button. Once the detent is pressed, we send 24 volts into an input, which then goes out to one side of our DCV to push the cylinder up. Then on our other side, once the upper sensor is read, 24 volts is brought over to the input, and the output brings it down. So now the second part will be the pneumatic side with the air, aka also the push that made this climb the ladder. Alright, for the pneumatic side, we're bringing air in to 75 psi regulator, bringing it over to our manifold to supply our DCV. Bringing it out one side and up to the lower side of the hydraulic, and then the high side goes to the high side of the hydraulic, and they are exhaust controlled by control valves. So some of our challenges in this project were we wanted to go as simple as possible, so we stuck with one double acting cylinder. The problem was when we did the 2 feet, we wanted an idler foot and a climbing foot from the beginning. The problem was making them in SolidWorks, you really didn't know what degree of angle or length that you wanted to go for to be good enough to climb and spring back and have enough clearance everywhere. So when we made these feet, we really looked for the bolt size and the stopping. We weren't too concerned about the length. Now, when they came out, they were definitely a lot longer than we expected. So we did have to do a lot of trimming and cutting, and actually, in the outcome, our bottom foot actually has a notch in it. It doesn't sit on the bottom of the foot, it actually sits on the end of the foot. Another problem we had was, since these feet were so long, even when we trimmed them down, we had a problem with our shaft of the cylinder not being a long enough reach when fully extended. So we tried making a coupler, and we just couldn't find one because it's made out of 1/4-28 threads, which is very hard to find. Ended up last minute making one out of some 80/20 tubing, and was able to have an adjuster screw about 2.5 inches long on top to adjust our whole top head where our foot stands. So another problem we have is with the wheels. We only had a single row of wheels, one on each side. The problem with that was that it pivoted too much. And then our final problem we really did have was with the foot at the top staying straight, not spinning around when the hydraulic or pneumatic was extended. So How we fixed all these problems was, one, with the wheels, we added a whole second row of wheels higher up to give it a lot more stability towards and away from the ladder. We did 2 guide rails that were actually where the wheels were mounted for the foot to stay straight, so it would line up in close to 90-degree angle or perpendicular with the ladder rungs. Also, like I said before, we put the block in for a coupler. We would have rather got an actual coupler, but that one worked so well that we didn't worry about it. And then finally, for our feet, we shortened them and we notched them. And that gave us enough room when the hydraulic was fully extended to hit both rungs, 2 rungs in between them, and for it to successfully climb up the ladder. So here is our second design, also our final design that was operational on the final day. As you can see, it has the second rung of wheels, feet trimmed, our coupler in place with the adjuster screw, adjusted properly to run slow or fast up the rungs, and also it has our guide rails set up so the top foot stays straight. So as you can see here, here's our robot climbing in a slow motion. What I mean by that is our directional control valves for the exhaust are trimmed down so it can allow exhaust slowly. As you can see here, we hit every rung with actually both feet, and our idler foot locks as our top foot goes up to the next rung. Our bottom foot started on the first rung, and our top foot started on the 4th rung. This took about 20-25 seconds to climb. Here's our fluid sim. This is showing our operation of our device. We did use a fluid sim EasyPort system, so it is controlled by the computer. As you can see, it is a very simple system. We're only using 2 ports of our EasyPort. Our button is a detent push button. Once that is pressed, our 1B1 sensor, or lower hydraulic or pneumatic piston sensor, is engaged, which then pushes our pneumatic cylinder up to a maximum. Once it does hit the maximum, our 1B2 sensor is engaged to bring it back down. When the 1B2 sensor is disengaged, we have a 7-time counter on it. Once that gets to 0, or 7 cycles of the hydraulic, then the system will shut down, aka at the very top of our ladder. Our pneumatic side, as you can see, is a lot simpler. All it is an air supply running to a double solenoid DCV. One side of it goes to the lower side of our pneumatic piston and the other to our upper. We do have 2 control valves, one on each line, controlling the exhaust of the pneumatic cylinder. You also see that 1B1 and 1B2 are above it. That is our sensors, sensing when to engage extension and when to engage retraction. Some things we learned on this project were that to keep it as simple as possible was the biggest thing. What I mean by that is you are using pneumatic, electronic, and mechanical parts. Mechanical for your structural, pneumatic for your driven, and electrical to drive your pneumatic. So the simpler you keep it, the better it's going to stay, easier and more reliable. So as you can see here, this is our motion control diagram. Once our detent push button is pressed, it sends energy to 1B1, which is active. Once that is active, the pneumatic cylinder starts to extend, which then is deactivated since it's magnetic. Once it finally gets to the top, 1B2 is energized. Then once it starts to retract back down because of 1B2, they are both de-energized. Once it gets to the bottom, it repeats that process. Once that D10 is pressed, as you can see, everything goes off. So as you can see in this picture, this is our bill of materials. And as our robot did look very simple, simplest in our class, there are still a lot of parts that go into it. First, we have various VEX materials, U-shaped, angle iron, flat pieces, various hex, screws and nuts, and various shafts and couplers to hold our gear wheels on, all supplied by the VEX. Secondly, we have our single double acting cylinder and various air lines for it. We also have various lengths and colors of electrical wires to connect our DCV, our easy port, our switch box to our 24-volt power supply. We also have in the middle there 2 sets of reed sensors, magnetic reed sensors. That is what was used to detect the extension, fully extended, and retraction, fully retracted parts of our hydraulic. We also have our regulator used to bring our air pressure down from 150 to about 70-75 psi. We have our DCV next to that to control which way the air will go out of it, either for the extension or down to the retraction. We have our manifold sitting next to that, which was used to bring the air from the regulator and then split it up, which we did not really have to split it up since we only had 1 DCV to supply. We also have, in this picture, various tools that came with our kit to put it together. Right below that is some of our handmade parts, including our 2 feet, which started off the same, but are now actually slightly different. We did have to have them in different lengths, and one actually has a notch, sort of a locking mechanism, where the other one was used to grab on top of the rung. Below that is our coupler that was threaded to 1/4-28, so we could extend our hydraulic or pneumatic cylinder. And also below that, to the left, was one of our screws that we used to extend that shaft and to adjust it. The cord in the middle goes along with the stuff in the top right hand corner. That was our easy port that was used to connect our electrical to our computer so we could run the program on FluidSim. We have our relay box or breakout box, the actual FluidSim, or not, the easy port, and then the connecting cable below it. Then over in the top left, we have our 24-volt power supply, and next to that, farther over, we have our switch box. So a lot goes into these when you're building these, because you are combining, once again, electrical, which is more in our middle there, your mechanical, which is down below, and pneumatic, which is to your left. So there is various parts here to make this run and function. I think some things we would have changed in this project, probably the biggest one would be to do a dual cylinder next to the other one, also with 2 feet, 1 idler, 1 lift, but then have them at a slight difference in height, so we ensure that we have maximum climbing efficiency. At least one of them will grab every time to ensure a good climb. You can see here, this is our fastest possible time we could do. To conclude this project, it was a very interesting one. Once again, touching back on that it does include all 3 separate elements of mechanical being your structural, pneumatic being your power, electronic driving your pneumatic. So this was a very interesting project, but also a very good learning project that touched on